There's one more application of the cross product, and that is in the definition of a triple scalar or a box product. So right here, we have u cross v dotted with some vector w. So vector u cross vector v, that is a vector output. And a vector dotted with another vector is going to give us a scalar output. So this is going to be a scalar in the end. According to our properties we listed prior, this is the same as writing u dot v cross w. All right, so that's the same idea. They mean the same thing. So just go back and make sure you review the properties of both dot products and cross products, which we've talked about in previous videos. So the matrix setup for this determinant that we're finding is very similar to what we were using for the cross product, but instead of ijk as my top row, we've got the components of vector u, the top row, components of v, the middle row, and components of w, the bottom row. All right, and so as I said, these are all going to be numbers, so we're going to end up with a scalar value here. So reiterating that, u cross v gives us a vector, and this vector dotted with another vector, w, the dot product produces a scalar. The absolute value of this determinant, which is a scalar value, the absolute value of that represents the volume of a parallelepiped, right, which is a parallelogram-sided box. So finding the volume of this parallelepiped, the volume is the area of the base times the height. The area of the base is the magnitude of those two vectors forming the base crossed. So u cross v, find the magnitude, that gives me the area of the base. And then my height is being determined by my w vector. And rotating that in this direction toward the perpendicular vector u cross v, we're going to find that height by the magnitude of w times cosine of that angle between the perpendicular vector and my essentially height vector w. So that gives us this formula, the magnitude of u cross v dot w. And in this case, I say magnitude, but we refer to those as absolute value of bars because this is going to give us a scalar. It could be positive or negative, and whatever that is, we're just going to turn that into the positive value. And since this triple scalar gives us a volume, that's a reason why, because of this geometry, we also call it a box product of u, v, and w, because essentially it's creating a box-shaped figure. So let's do an example. Here, we're going to find the volume of the parallelepiped determined by these three vectors, u, v, and w. And in order to find the volume, that's going to be this triple scalar. So it's the cross product dotted with the height vector. So the cross product of the two base vectors dotted with the height vector. So that means what we want to calculate here is u cross v dotted with that vector w. And the way we set this up is we are going to make our 3 by 3 matrix using the components of each vector. U goes in the first row, so I've got 1, 2, -1. V in the second row, -2, I have 0j and 3k, and W in my third row, I have 0i, 7, and then -4. At this point, we're going to determine that determinant in a similar manner. I'm going to take this 1 and multiply it by the determinant of the matrix formed by those 4 pieces. So I've got 1 times the determinant of 0, 3, 7, -4. Remember, the second one's always a minus, so minus this 2 value multiplied by the determinant of the vector -2, 3, 0, and -4, and then plus -1 multiplied by the determinant of -2, 0, 0, and 7. So I have 1. Finding this determinant, I have 0 minus 21 minus 2. My next determinant is going to be 8 minus 0. And then I've got minus 1, this third determinant, -14 minus 0. So for that first term, we've got -21, then we have minus 16 and plus 14. -21 minus 16 minus 14 gives us -23. And that is a negative value. We said that the box product or the triple scalar, it's going to be the absolute value of this scalar that we get as a result. So that's going to be 23, whatever our unit is, 23 units cubed. And that's how we do a triple scalar product or a box product. As always, email me if you have any questions.